So I had gotten a request to go over one of the mindscapes. Let's go ahead and take a look at that. So here you're going to be given your own number of copies that you need to construct a version, and the scaling factor. In this one I have 8 copies and the scaling factor is 3, and we're going to find what the dimension of the object is to 3 decimal places. So you're going to have different numbers probably, but you'll use s to the d is n. So 3 raised to what power is 8? And now I'll need a number close to 2 because 3 squared would be 9, but not 2. So I can use the guess and check method. Since you all have different numbers though, I think I'm going to remind you of the other way to do this. So if you can get an online calculator to take the natural log if you don't have a calculator that does that. I know my calculator on my phone, if I turn my phone sideways, becomes a scientific calculator, and then I could do this on there.
So how do we get that?
So I'm going to type natural log of the number 8, the number of copies, and divide that by the natural log of the number 3.
How did you get the natural log on the calculator?
So mine has an actual button that says ln. So if you don't have a button that says ln, then you're going to have to get an online calculator if you want to use this method instead of the guess and check. It is much faster. And then I just have to round carefully to the thousandths place. So my 4th position is 7, which is 5 or higher. So since the 4th position is 5 or higher, I round the 3rd position to a 3. And that's just saying I'm closer to 1.893 than I am to 1.892. Any other questions?
Mine says, so like I did it for 9, and like n for me was equal to 7, and s for me was equal to 6. No, yeah, s was equal to 6. So then I got like 1.086, but I kept it. I don't know if I rounded it wrong or something, because it like just would not take anything I put in the answer.
So if you enter 1.086 and it's not coming out, then see me after class, okay, before you enter it again. Okay. Any other questions to go over? Yes?
Mine skipped 2.
Mine skipped 2. So here's a triangle along with some larger versions. What is the scaling factor for each of the larger copies? The middle version has a scaling factor of 2 because you see the base of your triangle is so long, and then you put 2 together, so that makes the base twice as long. Whereas over here you put 3 side by side, so that it's 3 times as long. So even though we don't have a ruler on the screen, we can pick out how many triangles wide it is. 2 wide or 3 wide. Any other questions? Mm-hmm. So this one we did in class on Monday, so it should be in your notes, and I'd be happy to go over it with you one-on-one if you missed it somehow. Anybody have any other questions? So this is in the 7.3 notes. Yeah, so the second to last one that we did. So we've been looking at pictures of the Julia sets. Today we'll take a look at visualizing the same idea in different ways to see relationships. So we looked at the Julia set by looking at the numbers in real detailed manner. Today we'll try looking at pictures instead. Of course, I don't have a way for you to make copies of the pictures, so you're going to have to read your book or look at the video again to review what we do today. Or work along with me. This was the app from Apple, Fractal Factory, and it reminded me to show you that there's a Julia set that goes with every single number. So you can type the numbers in up here for the numbers. Now remember, the numbers refer to points in the complex plane. So we're just going to review a little bit where the Julia sets come from. So if we put a Cartesian plane, an x and y axion here, then these numbers refer to the x-coordinate and the y-coordinate. And the x-coordinate was the real number, and the y-coordinate had an I on it. So this would be the Julia set that goes with 0.32 plus 0.44i. We created the Julia set that went with 0, and we look closely at that one. So here's the Julia set that goes with 0, and it was just a circle. Let's look at the Julia set that goes with 0.5i. So I'm going to have 0 plus 0.5i. I don't have to type the I on this application. And let's review how this Julia set is made. So there's a Julia set with every single point in the complex plane, and each Julia set is formed by taking and either including a point, which they color black, or excluding a point, which they color blue. So points that are colored black are included in the Julia set because when we square them and add the number that goes with that Julia set, 0.5i, and repeat that process over and over again, we stay tiny. So here, if I take the point and look at the complex number that goes with that point and square it and add 0.5i, and then take that result and square it and add 0.5i, and take that result and square it and add 0.5i, this number is colored black, so it must stay tiny. Whereas if I take this number out here that goes with this point that's blue, and I take that number and square it and add 0.5i, take the result, square it, add 0.5i, take the result, square it, add 0.5i, and keep doing that, it doesn't stays tiny. It goes zooming off and gets real big. The numbers in brown also don't get tiny. They go zooming off, but they go zooming off more slowly. And so that's why they're brown instead of black. So the colors are coding as to how fast they get real big versus black points, which are included because they stay tiny and small. As you square, add 0.5i, square and add 0.5i. So there's a Julia set with every number, and I'd like you to look at one with me together. So can you go to Canvas, please, your digital learning environment Canvas, and the link that I have there, please. This does work on Apple phones. I don't know if it works on Androids, but the students in the last class who had used it on their phone had no trouble with their Apple phone. So if you go to our Canvas homepage, then under the fractal generators, can you please pick Julia sets? So I'd like you all to get this up. I'm going to give you quiz questions off of this, and I want to make sure that you're clear on how it works so that you can so that you're able to do this, okay? Okay, so click on the Julia sets. Did anybody get this going on a phone? I just would like to know. So does anybody know if this works on an Android phone? Does nobody have Androids? I thought that Androids were like...
Wait, where did you put that?
So that's on Canvas,
Oh, I found it.
Julia sets.
Where did I just do?
So in this, we see the Mandelbrot set, which we'll be getting to in a little bit. And you can put the Julia set number that you want right here. So the Julia set that went with 0, you could just put a 0 in and hit enter. And there's the Julia set that went with 0. Now this doesn't put the colors down. In fact, it just puts the boundary of the Julia set, which actually is the correct Julia set. That we see these inside interior points colored black to help us understand how the Julia set's created on the fractal factory. But the Julia set itself is actually the boundary of all the points that are inside here. Okay, so you can put in the number and then clear and put in whatever number you want. So let's all look at the 0.5i Julia set together. So that's the one I had on the fractal factory. So put 0.5i and hit enter. So this is the boundary for all these points that inside have iterations of squaring and adding 0.5i that stay tiny. And you can see that by clicking on a point. So take any point in here and click on it, and you see that zigzag that forms? That's showing you what happens as you do the iterations. So we work all these iterations out with this Julia set for 0 with long, tedious math calculations. Here you can do it with a click of a button to see what's going on. So this, click any... Good, yeah, keep clicking and you'll see more and more. So I'm going to take one at a time. You can clear it if you want and do it over. So I clicked on this point, which is represented by a number in the complex plane. If you square that number and add 0.5i, the result is the number represented by this point at the end of the jagged line there. And then if I take this number and square it and add 0.5i, it brings you to this number represented by this point. And if I square that and add 0.5i, the result is represented by the point right here. So all these points represent complex numbers, and when you square and add 0.5i, you get this complex number. Square and add 0.5i, you get this complex number. Square and add 0.5i, and so on. And you see it gets tiny. It doesn't go shooting off. And I saw you were experimenting, and you were getting lots of them that all zoom in there. So all these points inside this Julia set, when you square them and add 0.5i, take the result, square it, add 0.5i, and take the result and square it and add 0.5i. You see the visualization of the numbers getting tiny. They all reach out to this point. This must be 0, 0 on the graph of this figure, and that must be where they're all headed there, 0 plus 0i. Now notice if you take a point out here, which would have been colored blue on my fractal factory. See? You square it and add 0.5i, and it goes shooting off. Gets big really fast. It's so big it's not on the screen. If I pick another point out here, square it and add 0.5i, and the result is too big to fit on the screen. Now if you pick numbers that were shaded brown on the fractal factory because they were close to the Julia set, click on one of those, and you see it doesn't go shooting off so quickly, right? So take this number represented by this point, square it, and add 0.5i, and you're still kind of small. Take this, square it, add 0.5i, still fairly small. Square it, add 0.5i, still kind of small, and so on. So this stays close before it goes shooting off, and that's why it's shaded brown instead of blue. So that's where the colors come in. How many iterations does it stay close in before it goes zooming off, changes the color on the fractal factory. But here you can actually see those iterations. Does anybody have any questions on this? You can do the same thing with the kind of boring Julia set that goes with 0. I hit clear instead of enter. So all the points in the 0 Julia set, when you square them and add 0, square the result, add 0, square the result, and add 0, you can see they stay tiny, stay inside. Whereas out here, you square this number represented by this point, add 0, it goes big. And then the numbers close in were colored browns, so they're close to the Julia set, but not in it. They have iterations that stay kind of small before they go zooming off, and so they're colored a different color, brown instead of blue, on my fractal factory. So I wanted you to be real clear on Julia sets before we go to Mandelbrot sets. Does anybody want another example of Julia sets before we do that? Okay, so one Julia set to go with every number in the complex plane. The complex plane is over here as well with the Mandelbrot set sketched in it, so there's two different complex planes. When I click on a number over here, the Julia set that goes with it shows up over here. So you don't have to type the Julia set number in here. So this is the Julia set that goes with negative 0.26 plus 0.0976i. Okay. So clicking over here gives you the Julia set that goes with this number in the complex plane, the Julia set that goes with negative 1.07 minus 0.64i. Well, what I'd like to have you be able to figure out is why these numbers are in the Mandelbrot set. Why are all these numbers in the Mandelbrot set? It's related to their associated Julia set. Okay, so I'm going to click on a point in the Mandelbrot set and look at the Julia set. And now click on a point not in the Mandelbrot set and look at the Julia set. Okay, so in the point in the Mandelbrot set, not in the Mandelbrot set. So see if you can tell me why, what's the difference between the points, Julia sets, what's the difference between the Julia sets that go with points in the Mandelbrot set and Julia sets that go with points outside the Mandelbrot set? Okay, inside the Mandelbrot set, Julia set, outside the Mandelbrot set. When you can figure it out, let me know. Okay, inside, not in the Mandelbrot set.
They're not closed?
Good, they're not closed. So the Julia sets which are all one set are, when they're all one piece, I should say, the Julia sets that are all one piece, their points included in the Mandelbrot set. But here's a Julia set that's not all one piece, and so its point is not included in the Mandelbrot set. So one piece, so the point is included in the Mandelbrot set, several pieces, so the point is not included in the Mandelbrot set. So I'll be giving you problems on the quiz where I give you a picture of a Julia set. I'll actually probably just take the screen image. And I'll try and pick one that's real clear, like something like this versus something like this. And I'll say, okay, you can practice. Practice now, okay? So I'll pick a point. You close your eyes while I pick a point. That's not a good one. Let me do a different one. Okay. All right, so open your eyes, and I'll say, this is the Julia set for negative 0.23 minus 0.42i. Is negative 0.23 minus 0.42i in the Mandelbrot set? And you'll have to answer yes or no. Okay, so what would be the answer here? Yes, because it's one piece. Good. Okay, close your eyes. I'll try again. Okay, you can open your eyes. This is the Julia set that goes with the point negative 0.9 minus 0.59i. Is negative 0.9 minus 0.59i in the Mandelbrot set? Yes or no? And what would you say here? No. Good. So that's how that works. Points in the Julia set make points. Julia sets. There's a Julia set with every point. If that Julia set is all one piece, that point is included in the Mandelbrot set. But if the Julia set is more than one piece, that point is not in the Mandelbrot set. So that's where the Mandelbrot set comes from. So these are beautiful images. You can find them in more detail and in color online at different places. I like this site though because you can see those iterations going on inside the Julia sets without having to work out all the algebra. Does anybody have any questions in this section about Julia sets or Mandelbrot sets? Okay. Then let's go on to chapter 8. In chapter 8, we start looking at probability. So we're going to be less geometrical for the rest of the semester, more algebraic, more numerical. So there's numbers behind the geometry we've been looking at, but we've been focusing on the pictures and the figures instead. Now we'll be looking more at numbers. So in probability, we look at how likely something is to happen. Probability, your author says, is one of the great triumphs of the mathematician because we're dealing with the uncertain and unknowable. For example, if you go to the casino, do you know if you're going to win or lose? No, you don't know.
One time I accidentally won $100 at a casino on accident.
You won $100 on accident because you didn't know you were going to win. That's right.
No, like I clicked the wrong thing that I wanted to click.
Nice accident. Or how about insurance tables? The insurance company has charged me a certain rate on my car insurance because they've decided how likely it is for me to hit a deer on the way home. Okay, so what makes the probability, the study of probability, a triumph of mathematics is that they're able to quantify what we admit we don't know. We don't know if we're going to hit a deer or not. We don't know if that driver is not going to be paying attention and is going to rear end us. So we're able to do a quantitative analysis with probability that's useful enough to make companies profitable, even though we don't know what's going to happen in any individual case. Well, let's take a look at this example. We look at strange results of probability in chapter 8.1, and then we look at how those results are calculated in 8.2. So first question, how many people are needed in a room so that the probability there are two people whose birthdays are the same on the same day is roughly 0.9. So we'd be looking at the same day and month. Probability, 8.1. So 0.9 probability is high. Probabilities are measured between 0 and 1, 1 being a certainty, 0 being not going to happen. Okay, so this is a high probability that two people have the same birthday. Now I'd like you to write down a number. You don't have to share it, although you can. How many people do you think we need to be sure of having a birthday with a 90% probability? So not certain, but 90%. So very likely. Anybody want to guess?
40.
Did you read the book? That was very good. That was very good. Okay, how many, what would be some other guesses? How many of you guessed over 360? So that's what I get mostly. How many of you guessed over 300? So that's what I would expect, because what does the pigeonhole principle say we need in a room to be sure of having a birthday? Remember back to chapter 2 in the pigeonhole principle? How many do we need to have to be certain of having a shared birthday?
366.
Yeah, 366 if we don't count leap year, 367 if we count leap year. So most people would guess over 300, but in fact, the number is closer to 40. Did anybody put under 100? Anybody put a number under 100? Did anybody put a number down at all? You're like, no, let's wait and see what the number is. It's turns out that it's 41, and we're going to see why that is when we get to section 8.2. But for now, we're going to test it by representing 41 birthdays. We don't have 41 people, but how many do we have? We'll pick a couple birthdays each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so why don't you each pick 3 birthdays? We'll be a little high because I'll include me as well so that we can work together. So we're going to have 48 people in the room represented. So pick out your own birthday and your mother and your father's if you know it. If you don't know it, one of your parents, you can pick a different one. Put them in order of day. What?
They should know their parents' birthdays.
And you can please put them in order of date. Like my dad's is the 8th, and that's the earliest, so I'm going to put him first, July 8th. And then my mom is the 26th, and mine's the 27th, so I'll put them in that order.
Yours is all July.
January, yeah. I expect lots of birthday cards this summer. Oh, I'm just kidding. So put them in order by date, because that's how we're going to go through, and it'll be easier to keep track if you've got them ordered by day. So put like I have 8, 26, 27, okay, increasing by days. Okay, all right. Everybody have theirs down? All right, okay, who put a birthday on the 1st? Anybody put a birthday on the 1st? Raise your hands high if you did. Okay, not on the 1st. How about on the 2nd? Anybody put one on the 2nd? Anybody else? Okay, then we're not going to have 2 on the 2nd. How about on the 3rd? Anyone put one on the 3rd? One on the 3rd. How about on the 4th? One on the 4th. How about on the 5th? How about on the 6th? Okay, 2 on the 6th. What month? December. July. Okay. 7th. How many are on the 7th? 1 on the 7th.
Well, I had 3 on the 6th.
You had 3 on the 6th?
I mean 2 on the 6th, sorry.
2 on the 6th. What was your 6th? December? What, did you have any in December?
July and August.
July and August. Okay. Okay, I think we're up to 8 now. I have one on the 8th. Anybody else? Okay, is yours, what's your month is yours? February. Okay. 9? Anybody on 9? Okay, 2 on the 9th. What month? February? April. 10? What month? May? June. Okay. 11th? Oh, 3 on the 11th. Okay, what month?
December. October.
May, December, October.
We're getting close.
We're on to 12. How many on the 12th? Okay, what month is yours? February? January. Okay, 13? 14? Oh, was that 13?
Yeah.
Anybody else 13? Okay, 14? Okay, what month?
January.
January?
October.
15? Okay, what month?
August.
Oh, but there's nobody else, so I don't know. All right, 16th? Anybody on the 16th? Have written down? 17th? Okay, what month? March? April? 18th? 19th? 20th? Okay, what month? March? October? 21st? Yes. October? Oh, there's not enough. 22nd? Okay, 3 people on the 22nd. What month? July?
Hey.
July and July? Okay, what was yours? August. Okay, 2 July 22nd?
I also had a June 22nd.
Oh, June 22nd?
And July.
And July 22nd.
Yeah.
Okay, so you do have a July 22nd?
Yes.
And you have a July 22nd. But yours wasn't June 22nd, was it? August. Okay. Okay, good. So we found one on the 22nd, representing 45 birthdays. So weirdly enough, you only need 41 people to have a 90% probability of a shared birthday. Most people would think you would need like 365 minus 36 people. So in this section, we're looking at thinking about situations that jar our intuition, can lead to new and important insights. The next situation we look at is in your textbook. And it's a 25-year reunion that we're at. Suppose we return to our 25th college reunion and we see an old classmate. Classmate, I have 2 children. Wonderful. Is the older one a boy? Yes. And at this point, she chokes on an hors d'oeuvre and collapses.
Oh no.
Reunion scene, take 2. Suppose we return to our 25th college reunion and we see an old classmate. Classmate, I have 2 children. Wonderful. Is at least one of them a boy? Yes. And at this point, she chokes on an hors d'oeuvre and collapses. So it doesn't end well for her in either scenario. Oh, not so good. So at the bottom of the page here, naturally, we have some concern for the respiratory challenges of our former classmate. However, we probably would be more consumed with the following burning question. What is the chance that our classmate has 2 boys? Is the probability the same in both scenarios? That's what I would wonder, right? Okay. All right, so what is the difference between these 2 scenarios anyways? What was the difference in the questions? You see it? Anybody? Yes.
Is it that one of them asked if the older one was a boy and the other one is if they asked if either one of their kids is a boy?
Good. So the first one asks, is the older one a boy? The second one asks, is at least one of them a boy? So let's go ahead and write those questions down. So the 2 questions were, is the older a boy? And is at least one a boy? So in both cases, we want to know what is the probability that our classmate has 2 boys? So there are 2 children. Now, when I gave birth to my children, you didn't get an ultrasound to find out if it was a boy or a girl. You didn't get an ultrasound unless there was something wrong. So when you gave birth, it was like really exciting to find out if you had a boy or a girl. In fact, you had a lot of yellow and green clothing given to you because of that. Okay. So for me, when I went to the hospital to give birth to my children, what was the chance that my child was going to be a boy?
1/2.
Yeah, 1/2, 50%. So does that mean on these scenarios, where the older one is a boy, there's a 50% probability that they're both boys? Or when their question is at least one a boy, is the probability that they're both boys 50%? Are they 50% in both cases? Are they different than 50%?
No.
So go ahead and write down what you think, okay? And then we're going to use our playing cards to simulate this scenario and see what we can expect for the probability. So write down what you think, and then we're going to take out your deck of cards and shuffle it really well. If you don't have a deck of cards, you can use a a card generator online. I saw some in the last hour at random.org, and I think you found one at Cast Lots. So I'd like you to deal out all your cards so we have lots of data. We're going to see in section 8.2 that the more data we have, the closer our relative frequency will come to what we calculate probability to be. Okay, so shuffle your cards well. You don't want the jokers in there. No jokers. Or find something online. This is your class activity, so you will need a picture of this, okay? So see what you can do with your computer if you don't have a deck of cards. So what we're doing is we're getting these in sets of 2 once you shuffle. Oops, don't want that one. So you'll need to know in your set of 2 which one goes down first, because that's the older child, okay?
What should I do with this online? Like, should I just take a video and generate cards?
You're going to have to take a picture of your notebook as you write down your sets.
Okay.
If you're doing this online, you'll have to write down your results. You can write boy, 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 girl. So the red cards will represent girls, and the black cards will represent boys. You should get all of them. You should get 26 sets out. Okay, so you need the bottom one to represent the older child and the top one to represent the younger child. So this would be both boys. This would be the older child's a girl and the younger child's a boy. This would be both girls. Here I have the older child a boy and the younger child a girl. Right here. So if you don't have a deck of cards, then you can generate these online. And here's the data that we're going to gather. I have it written out here. Okay. So you're going to keep track, once you get all these dealt out, you're going to keep track of how many sets were both black, how many had the bottom card black and the top red, how many had the bottom red and the top black. So you go ahead and work on that activity, and I'll come around and gather data as you complete it.
So how many pairs is that?
26.
All the way down. First draw.
So we're taking a picture of them all laid out, or taking a picture of the
All laid out. Only the people on the computer have to take a picture of their notebook because they don't have a deck of cards.
So like you just want to make like a big tally chart with those, essentially?
Yes. Big tally chart.
And that's all I'll have to take a picture of?
Yeah. Write tally chart on it, because that sounds,
But you have to take a whole picture.
otherwise I'll be looking at it going, what? Because most people put boys, girls, 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 but if you do a tally chart, that's certainly sufficient.
And with this information, we're supposed to do.
Yes, this is your 8.1 class activity. Make sure your picture's in there. Okay.
What if they're both red?
Then you don't have to put them in a tally chart because they don't fit our scenario. Unless you want to keep track of your 26, so you could put another tally for both red, but we won't count it. So you know when you get to 26 sets.
It's like this person is
If you have your tally completed, let me know and I'll come around and gather the data together. That's so cool that you can write on your, I don't even know what that's called. It's not a tablet.
No,
It's like a laptop? No. Kind of a laptop?
all of them.
This is the top part, this is the bottom part. But it doesn't matter, it's just
If you have yours figured out, just raise your hand, okay? And then what about both buttons?
Oh, both boxes.
Once I've gotten your tallies, you can gather your cards up. And if you have your picture.
I took it off that.
That's too bad. Did you get yours figured out?
Yes, and 6 are all black, there's one. And then black card on bottom, and there's 5 black card on top.
Did you get yours done?
I got 6 both black, 8 of them where the bottom was black, and then 7 of them where the bottom was red.
Did I get your numbers? Well, okay.
Oh, wow. So that both by each other. Huh? I did. Where is this? This is that.
The first, they always want to blow it, so it's the first one to blow it.
Who said that you're red?
Yeah. So you tally that, you tally all the buttons, not all of them, but
Yeah, I think
for older. Oh, wait.
okay, hold on, what? So wait, so both like that?
Oh, I did it wrong.
Wait, so we're cutting 3 tallies for 3 different categories?
Yeah, so it's,
So the first one's like, they're like right next to each other, they're single.
yeah, so you'd be looking at them in sets of two.
So that's a tally right there.
But these are both black.
Oh, I did it
That's
wrong.
another tally down here.
Right, both black. These would be both together. Both black and both red.
Yeah. So Two.
There's so many black and red.
Three.
It's a lot harder on the computer.
4. 5, 6.
Well,
Okay, so that's a 5, 6.
I'm going to just take what I have to work with because I would like to finish this before the day's over. So, here's what we have.
I got 10.
Okay, so I'm going to ask the first two rows to add this up. So row 1 and 2, add these numbers up, please. I'm going to ask the, this is a 10, by the way. I'm going to ask the third row to do this row, and the fourth row to do the last one. And then please check with the people next to you to make sure the sum is correct. So I didn't get everybody's because of time constraints, but we have a lot here. So I'm going to ask the first two rows, what'd you get here?
61.
61, you confirmed it? Okay. And how about the middle? What did you get here, row 3? 63, and did you confirm that with somebody? You had 63 also? All right, thank you. And how about this row? What did you have? 50, and you confirmed that with people? Okay. So we're looking at our experiment, which records relative frequency as a way to investigate probability. So we were first looking at the older is a boy. So out of those, how many were both boys? So the ones that were both boys, we had 61. That was the ones that were both black. And the older was a boy. That's in the 61 because those were both black. And it's also where the bottom card is black, so 63. So where they were both black, well, that had the older one being a boy. And where the bottom card was black, that had the older one being a boy.
Wait, so what photo is this?
So this is where, how many were both boys, where the older one was a boy?
No, for like, you said this was the in-class work. What? You gotta take a photo of it?
Yes, you had.
Which one do we turn that in under?
Can I talk to you after class about that? Okay. It's 8.1. See, 8.1. All right. So what do we have for that? 61 plus 63. That's 124. $49.49. So that's close to the 0.5. So the actual probability is 0.5. And our relative frequency showed that. So if that's what you thought the probability should come out to be there, you were right. Now let's see, is at least one a boy when we look at both boys? So both were boys in 61 out of all the cases. At least one was a boy in all three that I had you write down. So all three of these, the 61 plus the 63 plus the 50, those all had at least one a boy. So 61 had both boys out of the ones where at least one was a boy. That's 0.35. Weirdly enough, the probability that both are boys when at least one is a boy is 1/3, 0.33. So our relative frequency actually bore this out. So this 1/3 probability that both are boys when at least one is a boy, and the probability that both are boys when the older one is a boy is 0.5. They're different probabilities for these, and we'll see why that is when we look at 8.2. Today we just did an experiment to see what the results of our experiment would suggest for probability. In 8.2 we see how we calculate the actual probability. So that's your 8.1 class activity. Hopefully you got that in there, and I'll see you on Monday. We'll look at this further. Hope you have a good weekend. Pardon?
That was a lot to write out.
It was a lot to write out. It's much easier to just deal it out. We need your cards again on Monday.
And we don't have class on Wednesday, right?
No class on Wednesday.